Hello, this is John Wen. The title of the talk is $20 million problems for any brain models and a holistic solution, conscious learning. This is recorded for a post version of the paper. The outline, I first talk about conscious learning, then talk about 20 problems. The first is the image annotation problem. The second is sensorimotor recurrence problem. The third is a motor-supervision problem. The fourth is the sensor calibration problem. The fifth is the inverse kinematics problem. The sixth is the government-free problem. The seventh is the closed skull problem. The eighth is a nonlinear controller problem. The ninth is the curse of dimensionality problem. The 10th is undersample problem. The 11th is distributed versus local representations problem. The 12th is the symbol problem. The 13th is local minima problem. The 14th is the abstraction problem. The 15th is the compositionality problem. The 16th is the smooth representations problem. The 17th is the motivation problem. The 18th is the global optimality problem. The 19th is the auto-programming for general purposes problem, APFGP. The 20th is the brain thinking problem. Then I talk about conclusions and discussion. The brain problem is like brain man and the elephant. Conscious learning is the first algorithm. Before existing conscious theories exist, but they are not algorithms. They are schematic ideas. There are mainly three: theater of consciousness theory, microtubular theory, integrated information theory. The first conscious learning algorithm was published in AIEE 2022 by myself. This talk will talk about $20 million problems solved by the algorithm. The solution is holistic because it solved all 20 problems altogether. It's detailed so that it's implementable and testable. First, let's define the consciousness. According to Merriam-Webster Online Dictionary, the definition of consciousness has 5 levels. The first level is a state of being aware. A, something within oneself. B, external object state of fact. And C, social or political causes. The second level is the state of being characterized by sensation, emotion, volition, and thought. The third level is the totality of conscious state of an individual. The fourth level is the normal state of conscious life. And the fifth is the upper level of mental life. We like to give a systematic definition because the dictionary definition is ad hoc, it's a piecemeal. It does not help our understanding of the brain mechanisms. So the systematic definition of consciousness is awareness of longer and higher context than the immediate context. What do we mean by conscious learning? By definitions, the learner must be conscious of a longer and a higher context at each instant t, so as to be more conscious of longer and higher context at next time instant t plus 1. Developmental network 3 is for conscious learning. There are 3 generations. DN1 has embodiments WWN1 to WWN9. where what network 1 to 9, each has a static boundary of brain areas and has action symbols. Developmental network 2, each neuron develops its own computation zone. It has action symbols. Developmental network 3 is free from action symbols. Grow a network from a single cell and has a fluid hierarchy that is suited for any consciousness, and is the first algorithm ever for learning consciousness. We will revisit this architecture many times because it's a holistic solution. And the architecture is that you have a sensory input, and this sensor example is vision. You have color scene, you have object, multiple, A and B in this case. Then you have a motor, and a motor could be input and output. Right now, the motor, we denote 3 motor areas, each corresponding to a concept category. Here is a location category, the type category, and this is a combination of concepts called relation. And in general, you could have more concepts like scale, like orientation, and you have many complex relations. In this case, A acting on C, A acting on B, like that. And the dashed lines are hidden area of the brain, and we unfold it so that easier to see from low to high, where low means that concrete, high means more abstract. Here we have a basic concepts in terms of location and a type of object. Here is location of object A, and it has location of object B. The color indicates the type, and the location in the hidden area roughly corresponding to the location of the object. So you can see the invariance takes place where the type has a location invariant. The A type collected all the pink areas of the detection of the object A. So object A type is locational invariant. Similarly, the object B type is location invariant. But there's other concept like location, and each concept value should be invariant to other concept. In this case, location is invariant to type. So this location is invariant to all the types. And later on, you have a relationship between object A and B, and our object B in this case is a type, but it's related to the also location. And this object A is location this, and object B is location at that. So basically, each relationship between two objects A and B has both location information and the type. So early neurons, you have XZ as input, and early neuron is more concrete. And later neurons has only Z as input, in this case Z and Z here, and they are more abstract because action tend to be more abstract, but the action itself has concrete properties. For example, when I speak, every time my pronunciation different, although I learn different way of presenting the same idea, in this case, yes or no. So we do have abstract actions into meanings, but every pronunciation is concrete. So there's concreteness in sensory input, there is a concreteness in the motor input, but in general, the action tend to be more abstract. The variation is much smaller than the corresponding variation in the sensory input. In this case, the object A could be different location, different appearance, and different scale, and could be mixed with cluttered background. So we'll get back to that again many times in the future. 3 AI schools. There are symbolic schools, connectionist school, and developmental school. By symbolic schools, I mean the human post-selection of system after knowing the test set. For example, I know the micro word, and I expect the test set is for this micro word. Based on the test set, I generate a representation of the micro word. So that representation is a post-selection of the system representation after you know the test set. So symbolic word is very much conducting post-selection, means select of representation after you know the test. Connectionist ideas is also doing post-selection mostly, and machine doing post-selection, or human does a post-selection, or combination of both. The selection of a network based on the test set, and they train multiple networks, and after training networks, they select the luckiest network based on the training set or test set. There are two types of problem. One is the reporting only the few luckiest networks and drop the data. And the selection is often based on test set, all right? Although in principle, they probably don't say that it's based on test set, but in reality, post-selection is based on test set. So this is like testing on training set. Developmental school, in contrast, train a single network for lifetime without post-selection. And as far as I know, let me know if I'm wrong, our group is the only group that for each life only train one single network, which is true for perceptron and developmental networks. Let's move on to the first problem. In the annotation, where you train the network, you have input, you have collected scenes, in this case here. Then you can have other things that are not related to the object you are detecting, and use a polygon to click the vertices. So in closed area, you want the system to learn. You may have one object or multiple, but you also have a collected scene. And then the network only learn the area inside polygon. This is annotation, means that this is a person's name, for example, of human face. So this is annotation problem. It was widely used in ImageNet, and perceptron was the first system that used annotation. Then how to solve the problem? We say we do not need to do annotation. So when you think about the context, for example, that I'm paying attention to A, and I pay attention to location, pay attention to the type, I pay attention to the relationship, then the top-down process will point to the segmenting object. And that segmentation may not be complete. For example, when I talk about object A, I'm pay attention to object A, but I don't need to do segmentation for object A at all. Then I talk about the object B, then I don't need to have annotation of object B. That's a totally autonomous. Of course, at the beginning, when the child is very little and they cannot do very well, not be very skillful, not error-free, but gradually they improve. So learning must be autonomous. So then get rid of image annotation problem, because annotation problem has a huge problem of the post-selection, as I said earlier. So the theorem one is auto-attention. Image annotation problem is solved by the automatic attention scheme that unifies object recognition, object detection, and also object segmentation. Although segmenting object is not instantaneous, but rather sequentially based on the intent of the recognizer or the learner. The second is sensorimotor. What do you mean by sensorimotor recurrence? So suppose over here, I need to make left turn, I turn my head to left, then you see the lane here, or you see traffic here, whether you have an obstacle. But if I make right my attention to right, then I see the object here, I see the lane here. So in other words, what you see depends on what you want to do at current time. The sensorimotor are highly recurrent. It's not like you collected images irrelevant to your action. So your action must be carried out before you can collect images. And statically collected images are wrong. And the learning must be on the fly. And it's not a batch collection of the data. So the big data has a flaw because learning is not on the fly. All publicly available data set, including ImageNet, are flawed. So how do we solve this problem? Because network is learning on the fly, and the action is executed to the real world, left turn, right turn, pay attention to the location, pay attention to the time. Then the next image will grab from the real world. When I move my head, for example, the image will change. So learning is on the fly. Theorem 2 is about big data flaw. Any batch data sets are flawed because of their violations of the sensorimotor recurrence principle. Theorem 3 is about on-the-fly learning. Grounded and on-the-fly learnings satisfied the sensory motor recurrence. Motor-Supervision Problem. The traditional learning, you need to provide class label or action vectors or give reinforcement. So they are tedious, only for some course actions, find actions impossible, give example, attention, for example. It's not possible internal attention. Another find action is like I'm paying attention to my prosody. So this kind of attention cannot be supervised. So free from motor imposition or supervision, when the system learning in real time, the action was generated autonomously by the learner. So there's no need to generate actions by the teacher. And the motor are totally autonomous. Theorem 4 is about motor-unsupervised learning. Motor-unsupervised learning solve the motor supervision problem because the action is self-generated and there's no need to provide the class label, actions, vectors, or even reinforcement signals. Sensor calibration problem. Here there is a well-known experiment by George Stratton. This is a new version of the glass that turn everything upside down. And if you see everything upside down, and the human has problem generating actions because the mapping was wrong, but the human is able to learn interactively after about 2 weeks, human can react correctly. So in other words, mapping was learned online on the fly, and the sensor is calibrated automatically. So our method will not need the sensor calibration. So whatever the sensor you have, then the action is based on the attention of the image patch that acquired from the network. So the learning mapping will be automatic, like the experiment earlier. But of course, we have not demonstrated that capability yet because the learner must acquire sufficient skills for learning. Theorem 5 is about sensor calibration. If handcrafting machine consciousness is impractical, autonomous sensor calibration requires conscious learning. Inverse kinematics problem. Here, if you are given position and orientation of the end effector, then you need to solve the inverse kinematics problem so that the angle of all the joint must be solved. If the arm is not redundant and the solution is unique, but if the arm is redundant, this means that you have more than 6 degrees of freedom, then the solution is infinite. And it's easier to derive the location and orientation of the end effector from joint angles. This is called forward kinematics, but the inverse kinematics is much harder. And this is typical solved in robotics. But human does that? No. Baby attempts to reach, right? It does not do all the freedom, of course, in early arm. The action are kind of clumsy, but baby will learn reaching, pre-reaching, and during the early days after birth. So solve inverse kinematics problem will allow the network to interact with the object, then learn the kinematics of the hand, of the body. Theorem 5 is for motor calibration. If handcrafting machine consciousness is impractical, autonomous motor calibration requires consciousness. In other words, it needs volition. You need your action based on what you want, and so that you can try your motor actions. In the meantime, you are calibrating your motors and your body. Government-free problem. Internal brain does not have a government. So map of a body surface on the brain cortex is generated on the fly. So there's no government that controls the representation of the brain. There are 3 cases about the government. If a government designed symbols within a network, for example, CNN, STM, and assign the symbol to some individual neurons. For example, gate. This human is a government within the network since he is aware of the task and he organized the architecture after knowing the task. Case 2, if a human design a function block diagram, like very typical people draw, oh, this is the sensory block, this is the value block, this is a critique block, and assign load of the blocks. Here, Stratton and Prasad in a journal of machine consciousness, and here's a diagram, and this human that he designed that also is government within the network, since the human is function aware for each concept or each block. So in this sense, the machine is not really doing consciousness because the consciousness is limited by the block diagram designed by the author. So it's not for any consciousness. Case 3, in Symbolic AI school, a human programmer designed symbolic representation for a task that assign network. So this human is a government because he is a task aware. Theorem 6 is about solution to government free. A conscious learning system must be government free. So how do you get government free? Here is architecture. And we grow network starting from a single neuron. Single neuron, including sensors, muscle, and hidden areas. Then you will split into a sensor neuron, motor neuron, and internal neuron. That's only one start with, one for each, sensor, hidden, and motor. Then it will grow, and 1 become 2, 2 become 4, and the growth will be exponential, like biology, and the representation will be smooth. And during the process, each neuron is autonomous. There's no government. So that's a simulation of biology. Closed skull. Skull is closed after inception. Skull is off limit to direct interaction by the teachers. Teachers outside womb, and after birth, teacher is outside the skull. Human trainers are not allowed to tune network parameters. So that's in contrast with CNN and long short-term memory, LSTM. So how do you solve the closed skull problem? So you allow the system to generate representation on the fly, including how many neurons and connection patterns and the other parameters. I will get to that later. Closed skull, 7. If all hidden neurons inside the skull learn unsupervised, the system solves the closed skull problem because everything inside the skull is fully automatic from the signal from sensory effectors and other hidden neurons. Then solve the closed skull problem. Nonlinear control problem. And suppose that we have a controller that for space shuttle, for example, and you design a functional diagram, you have block diagrams, and nonlinear means that each component is nonlinear. Nonlinear problem is an unsolved problem in control community. The way we solve nonlinear control problem is Turing machines. Turing machine is not for neural networks. Originally, it's a model from Alan Turing for traditional computers that are symbolic. But we extended a Turing machine to become emergent. And then you can learn an emergent Turing machine by sensory inputs, which are vectors, and a motor input-output, which are vectors. Then you have internal representations. And in the traditionally symbolic Turing machine, it does not have internal representation. It has only a lookup table, you do search, symbolic search. But emerging Turing machine has internal representations. Here you have early hidden areas and you have later hidden areas. So the control of a Turing machine is an FA. And suppose that you have a Turing machine, and if we look into our mapping, the traditional Turing machine has a state, then tape symbol, and a new state, set of new state, and upper tape symbol, and head motion, left, right, and stationary. And we design so that we consider the sigma prime as a union of the tape symbol. Then the new state space, Q prime, we expand it so that include not just the original state, but also the output state, which is the action, and the head motion is also action. So include both state and the action. You call it a new state. Then you can see that the formulation of the transition table for this machine becomes an FA, right? FA is the state input, go to next state. The fundamental advance from the proof is to expand the state. So the state, including not only the internal state, but also the motor actions. Definition 9 for general purpose control. What do you mean by general purpose control? At any time of operation, a general purpose controller decides what task it should take up, what goes, how it executes the task, and what to do if it executes the task well, not well, or a new environmental situation occurs so that task should be changed. So this is called the general purpose control. It does not start with any particular control task, but rather it pick up the task and also decide the criteria of task execution, whether it's doing well or not. Theory 9 is about general purpose control. If handcrafting machine consciousness is impractical, general purpose control requires conscious learning. The cause of dimensionality problem is discussed by many researchers, and probably some researchers have different interpretation of the cause of dimensionality, but most popular one is that if the number of features increases, then your performance will increase. But gradually, when you continue increase now features, then the performance will drop. So the cause dimensionality in this case is number of features, how many features you want. But cause dimensionality could be also related to the number of pixels, dimension of input. And how we solve this problem? And we do not have a monolithic feature at all. And the more feature, the better, because the system learns and hierarchy of representation on the fly, and the more resource you have, the better. So we do not have a cause of dimensionality problem. Theorem 10 is about solution to cause dimensionality. A hierarchy of features at multiple levels of the hidden layers or areas, which are concrete at low levels to abstract at high levels. Low level means closer to sensors. High level means closer to motors. And this hierarchy addresses the cause of dimensionality problem. However, the hierarchy is not a cascade like CNN, but instead a complex network where a high level concept may connect to and from any low levels. The low levels, the scale is small, and the high level scale is bigger because the type, for example, is applied to any location in the sensor. The undersample problem. What it means that we have a few samples in learning. All right, in spatial language, one example should be sufficient. And or human children generalize well from few samples. How do we address this undersample problem? In contrast with data fitting in the traditional neural networks, we learn rules. And the rule is the rule in the Turing machines, and the rule will apply to the different data setting. So it's rule-based. You learn domain rules, knowledge rules. So generalization and transfer takes place. So it's theory 11 addressed with this undersample problem. The feature hierarchy in theorem 10, which is about cause of dimensionality, enables successful generalization from undersamples. And one sample sufficient, for example, a language issue. Distributed versus local representations. Suppose you have an area, now in this case, neuron representations. 5, 5, 5, if all the neurons in an area is firing, that's distributed. And if on one neuron, few neurons are firing, then it's local. The distributedness is defined as follows. Suppose you have a brain area A, and you want to define the distributedness of area. Y is a response pattern of a particular time, Y1, Y2, up to Yn. This means that you have n neuron in the area A, and distributed of a particular vector Y is represented by the probability distribution, where the firing pattern of Y, whether the Y1 is 0 or 1, then S is the sum of all the values, so that you compute the probability. And you compute the probability of the response divided by the sum of the expected response. They have a probability distribution for each neuron I to fire. then the distributedness of the representation of the area is when it is related to the entropy, where H is the entropy as defined originally. Then the P is a probability for particular Y pattern to occur. And all particular pattern Y can happen in the A, and all possibility of Y can occur. Then you do a probability weighted entropy. That's our distributedness. Theorem 12 is about non-uniqueness of meanings. Each hidden neuron does not represent a unique meaning. So that's related to the distributedness of neurons. So you do not expect that a neuron represents a particular meaning, even in motor area. Regardless of the representation of the area is highly distributed or local. So what do you mean by no unique meaning? Suppose that I have a hidden neuron, for example, here, and this particular neuron has a location at this particular location, and has also another meaning, which is the type, which is of the A type. Color is the type, and the location in the plane means location. So this neuron here does not have a unique representation in terms of the meaning. Here, motor neuron, for example, right? The motor neuron here does not really mean that a particular location. Even in this particular case, we say it's a collocation, the neuron corresponding particular location. But real situation that this may be related to our arm. So the neuron control the aiming action of the arm. So the arm is not just for location, but also related to reaching, for example. So reaching and the location have two meanings for motors. For example, this is the vocal tract, for example. I say A and B, but my particular action of the motor in the vocal tract, they're corresponding to different meaning. For example, suppose a particular sound A and B all use the same muscles. So in the motor areas, each muscle does not correspond to a unique meaning. Symbol problem. What do you mean by symbol? A reviewer confused. He said that stop sign is a symbol. No. That's not in computer science. For layman, yes, maybe confused, but by symbol, we mean a particular computer representation. Typically, it's ASCII string. But does not have to be typed to ASCII. Could be any version of the symbolic representation in the computers. And the sign, in this case, a stop sign is the object. It's not a symbol. This is because a stop sign can look different, right? Different angle, different distance, different angle has different look, and a different distance has different scale. And also it depends on lighting. Different lighting have different appearance. ASCII symbols and muscles. What do you mean by definition? The ASCII has symbol like A is 10001, B and 10010, and each ASCII code extended has how many? 1, 2, 3, 4, 5, 6 bits. All right. So it's unique. If compared to capital A, and they are unique. And the two symbols are exactly the same or different. If they are different, there's no distance defined. And they are exactly the same or different in the original ASCII definition of the symbols. But muscles, there's no unique representation meaning, as we said earlier, and maybe many patterns correspond to the same meaning. Even when I say A, I use different vocal tract configuration to pronounce the same symbol, in this case, A, for example. So definition for symbol is a token that a human program uses in design document to specify a meaning to other humans, typically described in a natural language. So it's for other humans to learn. But not for machine to understand. Machine had no idea of your symbolic representation, what you mean by symbol. all right? Symbol like ASCII, and when we make A, B, O, U, T, it's about, it's a string of letters, the symbols, and the meaning of about, human understand, the machine does not understand. The definition of emergence is a representation is emergent if it is directly generated from sensors or motors or hidden area that takes input from sensor and motors. And the sensor could include the biosensors, and biosense by definition is a pen and sweet sensors. It has values. Originally, the pixel value intense does not have values, but the biosensors, for example, pen sensor and sweet sensor has value, and human has prenatal preference for a particular signal. Definition about symbol problems. Symbols do not ground the word automatically at any time. So that's called a grounding problem. The symbols are not grounded, no matter how you argue about it. Many people said that as long as a symbol is derived from sensors, that's grounded. No, it's not, because the symbol is not grounded. So nor do they ground cross times. In AI, there's a frame problem, and the symbol need to be related at different time frames. That's also a grounding problem. Although they discuss in different contexts, but they still boils down to the same problem of symbol. So symbol should not be used at all. Symbol never grounded. Theorem 13 is about the symbolic impoverishment. If a machine does not learn any longer and higher context beyond the whole set of touch symbols, the set of symbols is impoverished. For the system to be conscious of all the touch symbols while processing sensory responses and motor responses. So in other words, if you have a symbol, although you learned a particular response from symbols, for example, treated as action symbols, but the system still fundamentally limited because it cannot learn many higher and longer contexts. In other words, that the learner is impoverished because of use of symbols. And the human is not, all right? Human does not have any symbols inside the brain. Local minima problems. We discussed why neural network have a huge problem with local minima. Typically, all neurons take random rows if you start the random initial guess. And it does not have a global plane. Neuron does not have a global plane. If you have a global plane in artificial neural networks, then it's doing human specified learning. Many rows are missing because the neuron need to learn. Without competition in CNN, so the problem is even worse because you have competition, then there are some competitive relationship between a set of neurons, and only have winner and our loser will not take over the roles. So without competition, the problem is even worse. Each initial random rows largely determine the final performance if you do error back plot. Then give example that in this case, you want to value of dark, this input is dark, then value of output dark is small. Then you want to say all the connected neuron help you, then all the neuron connected, means this one, this one, this one try to help, and this one not connected, then will not help. But example that this row has a certain, this neuron has a certain of neuron for the dark, but this doesn't, right? Although it's connected. Then you have problem, all right? This particular dark, this is not the dark we are talking about. Then if you ask this neuron to help you, then you are doing the wrong directives. So you have a huge problem local minima. The dice problem. A technique suffers from a dice problem if it requires a process of casting dice n times, n is larger than 1, and n systems are trained. You have more than one network trained and test around post-selections. In other words, the dice problem, because you do not have a deterministic procedure to give a one system. You have multiple systems, and each system is random. So misconduct from the dice problem is data deletion. Reporting only the luckiest few networks amounts to misconduct, data deletion. You must report all the data, and your performance should be the average of all the trained networks. And I produced reports on misconducts. I submit data deletion misconduct in AI papers to Nature, and data deletion AI papers in Science, and report to Communication ACM by authors here. Solution to the Nonlinear problem. We have a solution later on. That's problem 18, and it's a little bit earlier here. And we talk about global optimization solution over there to address the local minima problem. So it's not an exhaustive search and try many networks, and each starting when guessed and pick the luckiest one. This is the misconduct. Abstraction problem. Definition. The abstraction problem for an intelligent system, natural or artificial, is to produce abstract properties from a physical or concrete examples. For example, we have many cars and buses, for example, and they all boils down to vehicle. And but vehicles, there are other concrete example, could be bike and scooter. So abstraction must be learned from example, concrete example in the physical world. Exponential problem. If you learn from concrete word, there are too many if you do data fitting. If symbolically approached, the recognition, detection, segmentation problem from a cluttered word is exponential in terms of the number of sample you need in computational complexity. So how to do abstraction properly to address the exponential problem? The Theorem 15 states that the hierarchy in the Theorem 10, because of dimensionality theorem, abstracts from features in hidden area Y using a constant resource in memory and time without dealing with the exponential in the definition 14. So exponential problem is addressed using abstraction. Abstraction is the solution. By definition, compositionality defines vaguely in philosophy, states that the meaning of reading or writing a sentence is not present in the words of the sentence. Metonymy is required. Here, example that we will swear loyalty to the crown, but it's really not a crown, not a head. Compositionality solution meanings lies in the life experience, namely consciousness. You need to go beyond the sentence itself. You need a higher and a longer context. The solution is a network, for example, developmental network 2, applied lifetime experience as a sentence meanings during its conscious learning. The paper was published in ICCE 2022 and AIEE 2022. And this is a theory, and this is the algorithm. In order to do conscious learning, you need a source representation. This is raised many times for brain representations, but I formulated here. Representation in a brain are smooth in 3D. For example, here, the surface representation is smooth because face is close to hand, hand is to arm. So the far away body parts are far. It's a smooth, but the same thing is true for hidden areas, not just a body representation in terms of senses. So how to generate a smooth representation? A network, for example, DN3, in which the global smoothness is maintained from small to large so that newly spawned neurons are near their parents and start with the representation of the parents, namely using cost-to-find approximation. You start with a single cell, then you start to generate more cells by splitting, and the child will take the parameters and the location of the parents. So although few neurons to start with, but gradually it becomes more and more complex. The representation becomes more and more complex, but the smoothness is maintained. So local smoothness is always maintained. Motivation. A brain takes reinforcers and has various emotions. And how to solve the motivation problem? And a network, give example DN, bootstrap motivation through 4 classes of neuromodulators throughout the network. Here we have 4 classes that has value. For example, potassium and GABA, one is excitatory, one's inhibitory, they don't have value. They just generate signals. But 4 additional categories have values. Serotonin representing pain, dopamine represents sweet, acetylcholine represents expected uncertainties, and then the norepinephrine represent unexpected uncertainty. These 2 types are related to the novelty and certainty, and these 2 types related to reinforcement. And we have a algorithmic expression to specify how these 4 classes of neuromodulators are used in the computation and in learning. Global optimization problem. The brain learns incrementally but must avoid catastrophic memory loss. Because we have a smooth representation and then the optimality is maintained. The maximum likelihood is what we mean by optimality, and avoid search. It's optimal closed form solution. The optimality is more general purpose than and more powerful than solving a local minima problem 13. Batch maximum likelihood is such that suppose have a joint distribution of input X and theta is a system parameter. Theta in our case could be network parameters, resource, and how many neurons. Y is a hidden neurons. And you find the maximum likelihood density for the input, and you get the maximum theta, Y, and Z. So Y and Z are representations, and theta is the system parameters. But our learning must be incremental, on the fly must be incremental. So incremental maximum likelihood, that's additional constraint under learner, because you cannot collect the input without getting action out from Z. So then you really need to generate the Z at t-1, and you compute internal representation hidden at t-1, and take the sensory input at t-1, then you output your Z action. Then you generate the next X, that's incremental part. The maximum likelihood part is to maximize in terms of the Y and Z, those are the motor area and the hidden area and the system parameters. Then you find the closed form solution. That's the beauty of the DN network. And you don't need to do iteration at all. You find the best representation in terms of the Y, in terms of motor, that will be output. Then you also find the best estimate of system parameters, for example, weights. But it will not be able to live your life. For example, you will not say, I regret it. Oh, I'm sorry, I made a mistake, and I go back the next last hour to relive your life. You do not do that. So the local minima may exist in the teaching, for example. Teacher is bad. So local minima is in the environment, but not in the brain. Every brain is novel, is optimal. Next is APFGP. auto-programming for general purposes. A brain must learn to write a complex program for any practical purpose. And the solution to do that is a DN2. DN2 start to do that and learn a universal Turing machine. It's emergent. Current robots have not yet reached an adult age, and that is necessary to have sufficient mental skill to generate sophisticated program. For example, robots should be able to generate design itself, for example, can write a program. And a future conscious learning robot would read and write books, design dramas, for example, and make business plans. I would not be able to deal with this problem here because very extensive, as the reviewer said. And I suggest you read the paper, all right, in the International Journal of Humanoid Robotics. The one's probably most sophisticated, which is brain thinking problem. Over 30 years ago, Alan Turing asked, can machines think? The solution is there. A DN conducts brain-like thinking, including planning and discovery for any practical purpose. If a particular purpose doesn't really count, the thinking must for practical purpose. It's open-ended. And we have a paper, Wu and Wen in IJCN last year for complete theory and some experiments about machine thinking for general purposes. And a skill for thinking requires conscious learning. Conclusion and discussions. There are also other important problems not discussed here. So I just picked up 20 as convenient and popular, and people are interested, and I talk about here. There are other million-dollar problems too, not exhaustive. Biology at the brain scale is not only necessary for understanding a brain, but also critical for solving many engineering problems in the AI. So many people say, hey, I don't care. And it's not necessary I follow biological way. And from these $20 million problems, you can clearly see that conscious learning is necessary. It's not optional if we are serious about non-trivial AI problems. An effective solution to any of the $20 million problems is impossible without solving them holistically by conscious learning, as reported when AIEE 2022. Like conscious learning is non-theoretically sound because the algorithm, because the solution to the $20 million problems, we still have challenging in engineering. Brain size, brain noise chips that runs at about 100 hertz, because driving, for example, you need a fast reflection rate. Thank you very much.